Disruption is at your doorstep. Whether you're a Fortune 500 or a startup, you are always trying to innovate faster and keep those competitors at bay. So being in this Sears building is kind of a monument to what disruption can look like. But having Rice University here as the ones that are leading the way for the future, we're very excited to have the pitch of 7 companies, 7 ideas here. I want to introduce up Adrian Trömel from Rice University. Let's give him a round of applause, guys.
Hey, y'all. You've heard this spiel before. We're standing in the city that is the energy capital of the world, home to the world's largest medical center, as well as NASA's Johnson Space Center. Rice is fortunate to have played a small part in that, right? Founded in 1912, 111 years of history. My name is Adrian Trömel, and I run strategy investments for the Office of Innovation at Rice University. And you're going to get 2 opportunities today to see overviews of that groundbreaking work happening on campus. One, in the room just down there, is the Research Innovation Showcase. Some of the groundbreaking, cutting-edge, basic work happening on campus. And then right now, when I'm done talking, and I swear it's not going to go very long, you'll get to hear 7 pitches from projects right on the verge of spinning out and forming new companies. But talking a lot makes us thirsty. So first of all, you can say thank you to Enrich and to Sharon Pepper, who's sitting today in the audience. Sharon? There we go. For sponsoring the happy hour happening at 3:30 p.m. at Second Draft. So, what is Enrich? The raison d'etre of Pumps and Pipes is that at the intersection and interactions and collisions between people, between companies, and between industries, great things happen. And that is also where Enrich sits. Because at Enrich, if you are active in healthcare and you want to find a way to work with Rice, come speak with Sharon. Whether you need to find a partner, a research collaborator, a way to get funding for your project and work with Rice, Enrich is the way to do that. So, what's the Office of Innovation? And what do we do? Historically, Rice has a lot of accolades, but we're not here to talk about history. We can talk about that for a long time, from buckyballs, groundbreaking research in medicine, world-renowned research institutes, etc. But we're here to talk about the future. And the way Rice thinks about its future is in 3 strategic pillars. Those 3 strategic pillars are energy and climate, healthcare, and urban systems. And just like Kennedy, on September 12th, 1962, announced the big moonshot, we have moonshots for each one of the strategic pillars in which Rice works. You might have already heard about the biotech moonshot, incubating early stage companies and helping those get to market. Watch this space for the climate tech moonshot, for the same thing in climate tech, energy, decarbonization. And then right here in the ION, we'll be announcing social and urban design initiatives. But talking about moonshots, launch pads is all great. But what does that actually mean? So we think about the resources for Rice and for launching companies in 3 main buckets. The facilities, where you do things, the friends with whom you do things, and the funds, how you pay for all of that. So let's start with climate and tech. You're standing in the ION, heart of the ION district, which wouldn't be here without Jan Odegaard. And for Rice specifically, that space up there, we're building out the Nexus. It's the front door to Rice. It's a showcase, a workspace, a makerspace. Like any good front door, we can walk out of it and engage with you, and it'll be a place for you to come and engage with us. On the 3rd floor, we're building out 7,000 square feet for startups and investors because it's hard to find money in Houston. For facilities in healthcare, not only do we have the Bioscience Research Collaborative at the edge of campus, we also have the TMC Helix, which was recently opened, for lab space and workspace for innovation in healthcare. And then you have friends, who you do things with. So industry, who do you buy from? Who buys from you? Who do you collaborate with as you bring your innovation to market? Investors, who pays for things? And government, how do you make sure that there's a clear path to market? So on the industry side, we are engaging industry And if you are an industrial partner, come talk to me so that we can find and focus on speed and scale with commercially oriented research. Then on the investor side, we're forming the Rice Venture Network, and on government, we're ensuring that independent of your industry, there is a clear pathway to market, that the regulatory space is clearly defined. And then finally, you have funds. Ask, maybe at happy hour, and any one of the founders how long it took them to raise their first round of funding. Especially here in Houston, that's really hard. So we're doing three things. We're taking strategic positions in seed series A funds as a limited partner. We've done already 3 of those to bring capital here to Houston, because one of the gaps in funding here is actually that very first round, because not a lot of people have the wealthy friends and family, the wealthy great aunt or uncle who might be able to fund their first company. But we're also doing 2 other things. You might have heard of the One Small Step grant, because the one small step is that last step before you start a company. Very often, an investor might say, I'll invest, but run this one last experiment. A potential client might say, I'll sign the LOI, I'll buy your product, but show me this last bit of data. So we created the One Small Step grants just for that. And then watch this space for the One Giant Leap Fund, because that's for the giant leap into entrepreneurship. And with that, we'll be able to fund this launch of those new companies and be catalytic capital to start off. But you're not here to hear me talk. You're here to actually hear those who do the work speak. And with that, I have the pleasure of introducing Professor Behnaam Aazhang to speak about engineering and medicine and mitigating neurological disorders. Thank you.
As Adrian said, I'm Behnaam Aazhang. I'm a professor at Rice, and I want to talk to you about engineering and medicine. When engineers and medical professionals work together, great things happen. And this is just 2 of my favorite things that have happened in that space. And this kind of innovation has been going on for 50, 60, 70 years. All right? Now, cochlear implant, deep brain stimulation, and the list goes on and on. And the question is, what's going on now? Where are we today? I'm going to talk about 2 technologies that are complementary of each other, and I'm going to present them in the context of one disorder, even though you can imagine that the implications of these technologies cuts across many, many different disorders. The disorder I'm going to focus on is Alzheimer's, and we all know what that means. We all know what is that all about. Is a form of dementia which is much more extreme than a typical dementia, and is all about our brain's clearing system, waste clearing system, malfunctioning. Right? And outside the brain, outside the actual brain tissue, between the skull and the actual brain tissue, there's a fluid called CSF, as you see here, and that basically clears brain's waste. Right? And then when those fluids go through the actual brain, it's called lymphatic system. Basically clears the waste. And this is a depiction of what could be the healthy brain versus Alzheimer's brain. And our clearing system works like this, that in a young, healthy person, the brain's waste, which is basically poorly folded proteins, get trapped and they don't get cleared. All right? And then this is an example of a patient that is old, a subject that is old, and the one at the bottom is a subject that has Alzheimer's. Basically, the clearing system is not working well. There are a lot of waste going through our brain. All right? Now, most of this clearing system happens during our sleep. Therefore, if we have a sleep disorder, the problem gets exaggerated. And also, the disorder the flow gets even worse when you have a traumatic brain injury or even mild traumatic brain injury. Therefore, this particular case relates to many, many different issues that we may have. Now, the question is, how can we measure our lymphatic flow, our CSF flow? The only way to do it today would be to use a 7 Tesla MRI. And as you could imagine, that technology is not available to many people. it turns out that Methodist has more 7 Tesla MRI machine than many other countries, right? And it is very difficult to work with, but at this point is a gold standard in measuring our CSF flow or our glymphatic flow. And the question is there an indirect way to measure CSF flow or glymphatic flow? And obviously the answer is yes, otherwise I wouldn't be here talking about it. And you can do it by other modalities. In particular, we've been doing it at Rice using a number, and in collaboration with Methodist, using a number of different modalities like EEG, EKG, and many other things. And the idea is that collect the data and run it through some kind of a machine learning algorithm, and then infer the actual CSF flow measurements from that, right? And it's been, very, very successful, and we call this thing brain check, and it's possible that this technology can be put out there in the open market. And the second question, the second technology I'm going to talk about is what if the CSF flow is low? And that has been correlated with early onset of Alzheimer's, that if the flow is low, that could lead to early onset of Alzheimer's. And the question is, how can we improve the flow? And in many animal studies, it's been hypothesized that you could increase the flow using modulation, right? We go back to this picture, not that picture, this picture, that you could do deep brain stimulation to increase the CSF flow. But you could imagine that that is a very extreme solution to a problem that may happen in a few years, right? The question then is it possible to modulate the brain, stimulate the brain without being invasive, without penetrating an electrode deep inside the brain tissue? And the answer is maybe, all right? And the way we are thinking about this is using radio waves. This is an example of an antenna that radiates electromagnetic radio wave in a particular direction. What if we can do something like that and put a wave, a beam inside the brain tissue, and then try to modulate the brain tissues using this kind of wave? The answer is no, because this kind of wave does not elicit neurons to fire, right? Because it's just way too, the frequency is very high, and it doesn't allow the ions to move outside and create a spike. But what if you can have two of these waves interacting with each other with a difference of the frequency of 100 hertz? It turns out that in that case, we have shown via simulations that you can get response from neurons. Therefore, that deep brain stimulation that requires penetrating signals could now be duplicated with this technology, basically having two sets of beams interacting with each other, being outside the brain, and reaching down and stimulating the brain, and hopefully increase the CSF flow, and hopefully mitigating a number of different disorders, including Parkinson's and PTSD and many others. And tell you that all of the studies that we have done so far have been all positive, and the last step left is doing animal models. And that's where we are today. With that, thank you.
So if you work in healthcare or think there might be an application for minimally invasive or even non-invasive constructive interference, come talk to Professor Aazhang and see what he does in his lab. Next, I'd like to introduce Adam Farsheed out of the Hart-Gerink lab, a PhD candidate talking about Amino, 3D printing human tissues for drug development.
My name's Adam Farsheed. I'm a fifth-year PhD student at Rice University in the bioengineering department. And today I'm going to tell you about my venture Amino, where we want to 3D print human tissues for drug development. So the problem is that drug testing costs have skyrocketed to an estimated $1 to $2 billion for every drug that goes to market. And this is because 90% of drugs that enter clinical trials are going to eventually fail. For each of those drugs that fails, tens to hundreds of millions of dollars are spent to carry out those clinical trials. Within the drug development pipeline, candidate drugs are tested on cells and animals before moving into humans. But this is a flawed and outdated process. The question is, how can we better predict drug candidate efficacy? At Amino, we believe the answer is human tissue models. Towards this goal, I took an interdisciplinary approach, combining my mechanical engineering background in 3D printing with the expertise of a peptide chemistry lab that focuses on designing hydrogel materials that emulate the body. This marriage gives us knowledge from two very different fields and has facilitated the breakthrough technology that our self-assembling peptides represent. Briefly, our material is based off of amino acids, and it forms a matrix that looks somewhat like the extracellular matrix that's in our body. We recently published our patent-pending technology in the journal Advanced Materials. We can see here the remarkable properties of our peptide hydrogels, as the soft gel-like material doesn't collapse over large distances. We vastly surpassed the level of 3D printing that had been performed with other peptide hydrogels, which is limited to simple structures like this cylinder, and successfully fabricated complex overhanging structures and multi-material prints. We also showed that our structures could be used to grow tissue, with immature muscle cells adopting a tube-like morphology after growing for just 10 days on our scaffold, which is indicative of their differentiation. Our work exploded on social media, with my personal LinkedIn post currently having over 33,000 views and being reshared by the Rice Bioengineering Department, Rice University, and various independent news outlets. Our self-assembling peptides are biocompatible as they support cell survival and growth, biodegradable into natural amino acids, and are modular and can easily be modified for tissue-specific applications. Looking at muscle and nerve, it is clear that they are both designed to have cells bundled into aligned tissues. We believe that the key to growing muscle and nerve is to mimic their hierarchical and aligned structure, which is exactly what we've accomplished with our newly patent-pending technology. We have developed a fabrication process to 3D print aligned nanofibrous hydrogel scaffolds, which allows us to mimic the extracellular matrix within aligned tissues. When placed onto our scaffold, cells recognize and directly spread along their material's nanoscale cues, and by 7 days they grow to confluency. By combining our instructive scaffolds with human cells, we intend to generate tissues from the bottom up. Amino envisions 3D printing human tissues that mirror the structure and function of natural tissues for inexpensive, ethical, and predictive drug testing. I'm Amino's founder and CEO, and I'm joined by Jeff, a professor of chemistry and bioengineering at Rice University. Help Amino print the future of drug development, and reach out if you share a passion for revolutionizing drug testing. Thank you.
Thanks a lot, Adam. And with that, I'd like to introduce Eugene Chu, working on engineering cells for chemical reactions, gas-filled vesicles, out of the field known as synthetic biology, working in Professor George Liu's lab.
Good afternoon, everyone. My name is Eugene Chu. I'm a third-year PhD student in the Liu lab. For a while now, we've been thinking about creating a startup from our research, and I'm excited to announce for the first time publicly that we're looking to create Riser Bio. Our product will be genetically encoded nanobubbles for bioprocessing. Okay, so we're thinking about bioprocessing in the context of emerging therapeutics. So over the past few years, we've had the emergence of a lot of first-in-class therapies. So for nucleotides, you could think of the mRNA vaccines that happened during the pandemic, or a few years ago, we had our first CAR T cells that have been very effective against blood cancers. You'll notice that these emerging therapies are getting larger and larger, and they're actually getting more complex as well. They do stand to provide additional clinical benefit, but as these are getting larger and more complex, so do the production costs as well. If we quickly scale each of these classes by their market size, we have the traditional small molecules, as well as proteins that are currently at around a $400 billion market. On the right side, what we're gonna see is a lot of emerging cell and gene-based therapies where they're relatively small markets, but there's only a handful of approved products in each of these. Right now, what we're looking at is around 1,500 active clinical trials in this space, where really we're just getting started with these product approvals. I think a lot of us might have gotten sticker shock in terms of the price for patients for some of these new therapies. But at the end of the day, they are relatively still expensive to produce right now. So if we do a very oversimplified overview of the biomanufacturing process, typically what we're going to be starting off with is a cell culture. We need to culture these cells and then process this culture. Finally, in the context of therapeutics, purification is usually one of the most important and expensive steps. And then finally, we have our fill and finish, so it's packaged and ready to go. Throughout all of these 4 major steps, typically there will be some sort of recombinant protein-based reagents. So these are typically the biggest cost drivers for producing some of these emerging therapeutics. If we take a look at CAR T cells, for example, they did a cost analysis on the manufacturing costs, and if we focus just on the red, this highlights the reagents and consumable costs. If we look at these individual items, these are all recombinant protein-based products. So recombinant proteins can take up almost 75% of the total production costs of these emerging therapies. So basically the problem that we're outlining today is what I'm calling the recombinant protein dependency loop. So in order to fulfill that original biomanufacturing process, you have a bunch of feeder processes that go in to produce these proteins that are necessary. So we need proteins in order to make proteins or cell-based therapies, and basically there's no underlying way to reduce the price across the board. At Riser Bio, we think we could break this dependency loop, and really what we're trying to do is create products that make recombinant proteins more affordable. So our technology is built on gas vesicles. So on the picture on the right side, you're going to see a floating layer of these gas vesicles, and these basically rise out of solution from a cell lysate. So you don't need any filters, you don't need any columns or purification resins. These are the first self-purifying and genetically encodable protein that's out there right now. In the Lou Lab, what we're really good at doing is taking the specific genes that make up these gas vesicles and introducing additional sequences, properties, as well as other functionalities for any rising or buoyant-based process that we might be interested in to support the emerging therapeutic markets. I think one of the most impactful products that we're looking to create is a protein purification resin. Like I said before, purification is often one of the most expensive and resource intensive processes within that larger picture. And just like how gas vesicles are able to rise to the top, if we add additional affinity tags or binding proteins, we're essentially able to create a rising resin that is actually very affordable and cost-effective to make. So this work is led by Zhongru Li. So basically, he took his engineered versions of these nanobubbles, he expressed them in parallel with a protein of interest. In this case, we're just doing a green fluorescent protein. And then what you can see is that basically our protein of interest binds to these nanobubbles, and they're going to float to the top so that they can be easily isolated in the absence of additional equipment, purification resins, or any of these other recombinant protein reagents that are out there right now. You can see in the resuspension with 1x PBS, we have a very green floating layer, and everything below is very pure, and we can achieve purities that are relatively comparable to existing commercial products. We took it a step further. So instead of adding a short peptide affinity tag on the outside, what we did is stuck an entire antibody onto these gas vesicles, and it's the same idea. So just as we rise our proteins of interest to the top, we can isolate mammalian cells using buoyancy-based process. So what we did is we took patient blood from across the street, we added our antibody-based GVs, and we're able to float out T cells with over 90% purity, which again is pretty comparable to the commercial products that we're testing side by side. I think one of the best parts of these gas vesicles that I don't have too much time to go into today is that these are actually very sustainable to produce. These are totally protein-based. You don't need any additional chemical reactions after or post-modifications, and these are ready to go using very simple expression systems. So to support our vision in terms of sustainable biomanufacturing and providing recombinant protein-based reagents that are a little bit more affordable for all these biomanufacturing processes, we're currently supported by the 50 Years Climate Manifest grant to scale up our engineered GV production in E. coli. We're also a finalist in the Climate Biotech grant at Homeworld Collective, where instead of using E. coli, we're using a photosynthetic cyanobacteria that we think is a more carbon neutral or carbon negative host species in order to produce these gas vesicles. And at the end of the day, what we're trying to do is create sustainable recombinant protein-based products, and hopefully we could lower the costs across the board and hopefully to patients as well. And with that, I would like to thank Dr. Liu and everyone else in the Liu Lab, as well as our collaborators at MD Anderson who have been helping develop this towards the cell therapy side. Thank you for your attention.
Thanks, Eugene. That was fantastic. So one thing I don't know if you guys noticed, that 50-year EQT grant, those are actually venture firms that are starting to back pre-incorporation science. So the Liu Lab was the part of the inaugural cohort to receive that grant from EQT in 50 years. So with that, I'd now like to introduce Wil Thomason and Zach Kingston to speak about high-performance, low-cost robot motion planning out of the Kavraki Lab.
Hi, everyone. I'm Zach Kingston in Wil Thomason, and we're both postdoctoral research associates in the computer science department at Rice University. And we work under the direction of Dr. Lydia Kavraki, where our lab works on robot motion planning. And today, we're excited to talk about this new high-performance, low-cost method that we have. So, what is motion planning? So, motion planning is a class of algorithms that basically, given a start, a goal, a description of your robot in the environment, finds some feasible, safe, collision-free trajectory for that robot to execute to do whatever you desire in the environment. Now, motion planning underpins a lot of the autonomy that you see in robot systems. Anything that needs to interact with the environment, navigate, or move around the world is going to be using motion planning in some way. But these algorithms can sometimes be relatively slow, kind of on the order of seconds to find feasible motion because they can be relatively complex trajectories. Now, why is the speed important? Well, manufacturing is moving beyond just pre-programmed motions of the robots in an assembly line. They're moving to these fast, reactive, dynamic environments where it needs to be able to adapt to things on the fly, such as this, let's say, packing task from this company, Mujin. And beyond the factory, as I said, motion planning underpins all of robotics. So if you're thinking of something like an autonomous car that needs to be able to react immediately on the fly to this changing and dynamic environment, it's important for that motion planner to be able to be fast enough that it can react to anything that happens. And beyond applications that exist currently in the world, there's also a lot of things that are slowly making their way out of the lab. So for example, beyond just the 7 degree of freedom robot, like I showed you before, we can also talk about robots that have like 30 degrees of freedom, something like this humanoid robot, Robonaut 2, down at NASA. And you can see here, doing the motion planning for this system is quite complex and can be very slow. So having methods that have a better speed benefit, that works. Similarly, it's not just the scale of the system, it is the scale of the task. As robots move to addressing longer horizon tasks, so complex tasks like rearranging objects, cleaning your room, cooking a meal, it's important that it has the underlying ability to find these feasible motions fast so it can satisfy these tasks. And so how we address this problem, I'll let Wil talk about.
Yep. Concretely, we have introduced a new method of finding complete robot motion plans. It's about 2 to 3 orders of magnitude faster than the previous state of the art. If I can call your attention to the plots, these are logarithmic scale in time at the top there. We're in blue. The previous state of the art is in orange and green. We don't even touch their time distributions. Often, in fact, we're planning on the order of microseconds instead of seconds, etc. Now, we're able to do this without requiring customized hardware or even a power-hungry GPU, just on a single core of an ordinary desktop computer, because we've introduced new insights into fine-grained parallelism for robot motion planning algorithms. And this also lets us work on low-power computational hardware, something like a Raspberry Pi or roughly the computational power of your cell phone in 2010, something like this. And our code running on that low-power platform is still about 1 to 2 orders of magnitude faster than the previous state-of-the-art running on the full desktop. Moreover, we're not sacrificing solution quality to find these plans. We find almost exactly the same optimal motions, just faster. So we're quite excited about the potential impacts of this. Most directly to something like industrial automation, as Zach already hinted at, we think that we can use this technology to build industrial robot systems that can react to things like dropping a piece during an assembly task and immediately planning to pick it up and continue, or dealing with items that are slightly out of place on a conveyor belt, just more robustness and more flexibility to unexpected variation. This can also benefit in task reconfiguration. If you can rely on your planning system to find a path for a given task on the fly like that, you don't have to spend as much time at the start doing process engineering and sort of making sure that everything goes according to your plan. And then this also leads to direct decrease in costs. Not only can we run on cheaper, lower power hardware, but we can also use coarser, less high fidelity models or digital twins of the environment because we can rely on the planning system to do more for us. Outside of industrial automation, though, we're also excited about the applications to upcoming uses of robotics, things like agricultural robotics, surveying, inspection robotics, where you have these robot systems deployed out in the real world that need to be low power because they aren't tethered to mains on a building. They need to be relatively cheap because they might get damaged or otherwise hurt by something like rain. And we can run on cheaper low power hardware. We can also give these systems the reactivity they need to deal with unexpected circumstances in the real world. Our next steps for moving toward these applications involve continuing to speak with potential industry partners to make sure that our beliefs about how this technology can benefit them aligns with what they really need, as well as taking our existing code base, which is fairly good. It's enough for us to have recently submitted a research paper, but still research code. It needs a bit of refinement before it's a production-ready system to get to that stage. And we want to combine these things together into a proof of concept demonstration work cell, like you see here from Katy-based Tech Labs, where we have our system running on a real industrial robot platform, carrying out a real industry-relevant task to concretely ground the potential of this technology to a real-world setting. So, as I mentioned, we have a preprint up if you're interested in more details. The QR code will also take you there. Please get in touch with questions, comments, thoughts, whatever. We're easy to find just down the road at Rice in Duncan Hall. Thanks very much for your time.
Thank you.
Zach, Will, thanks a lot. So if you use robots, make robots if ABB is in the room, come talk to Zach and Will. And with that, I'd like to introduce Jeremy out of the Verduzco and Aegean labs to talk about PFAS remediation.
Hi there. My name is Jeremy Daum. I'm co-founder of Coflex Purification. Before I get into the work that we're doing with that, I thought I'd give a little bit of an overview of an issue that's coming up in recent regulations. Many of you might work in water systems, and this would be very interesting for you. So the problem we're trying to address is PFAS. It's a polymer that's commonly used in various household products, anywhere from cleaning products, cookware, even stain-resistant couches. It's used like that because it's an incredibly hydrophobic and durable polymer. And unfortunately, those properties make it so it does not actually degrade naturally in the environment. So as a result, anything that we have made in the past or will make in the future needs to be removed by us intentionally. Now, normally that's already not a great setup. However, it's also found that this polymer is carcinogenic to humans when ingested and environmentally hazardous. So it only makes sense that, oh no, this is an earlier version. Okay, I'm gonna be going around here, bear with me. It only makes sense that we have been increasing regulatory pressures across the United States, starting in some states, but also soon to be the EPA, to limit the amount of PFAS that can be available in industrial wastewater and municipal drinking water systems. This is expected to affect over 6,700 communities and cost over $200 billion to implement. So, as a result, my team and I have been working on a solution that can very simply take PFAS-contaminated water, pass it through our module, expose it to UV light, and result in clean, drinkable, PFAS-free water. The product itself is a photocatalytic absorbent. It has an incredibly high surface area. Just a couple grams of what you could hold in your hand has a greater internal surface area than an entire football field. And that gives us very high contact with any pollutants that pass through it. As a result, we've seen up to 99% degradation of PFOA done in a lab scale reactor in the Verduzco lab. And we've done that without any need for a recycle stream, just a single plug flow system. So, the reason why we're doing this is that we've been speaking with customers about current solutions that are being proposed. And what we found from their pain points is that current solutions are incredibly expensive. They're very difficult to implement, usually requiring very large systems with absorbents that have to be replaced on a semi-monthly basis. They're incredibly energy intensive. I've I've heard the analogy using a bomb to kill a mosquito, and it's not that far off as energy wastefulness. And it results often in a PFAS-contaminated waste product, which either has to be buried or burned. And the regulations regarding that are right now very dubiously uncertain. So that's why we have been we're trying to offer an all-in-one solution that not only absorbs PFAS, like activated carbon systems, but also eliminates it in the same stream. We are using a scalable material that can be mass-produced in a large variety of systems, and use less energy in order to break down PFAS than the other existing methods. And as a result, it is a far more economical system to implement to help you adhere to these regulations in the least painful way possible. And the reason why this is all being done is because the cost of not doing anything is so high. It is estimated that worldwide there will be a $17 trillion annual societal cost of doing nothing. So as a result, US government and a lot of regulatory bodies have been massively increasing spending to try to find a solution to this problem. It has resulted in what we expect to be a $4 billion addressable market in just industrial water systems alone that we hope to capitalize on. And a market that large does require a very good team to help handle it. And fortunately, I've surrounded myself with some very talented people. First, we have Dr. Alec Einstein, a recent Rice graduate and founder and lead organizer of Proposition B that passed here in Houston just last month. We have Dana Vasquez, who is a MBA candidate working with us on marketing and commercialization. She has been previously a PFAS remediation consultant at ERM and is currently sitting on the Houston Clean City Commission. And then myself, my name's Jeremy Daum. I'm a fourth-year PhD candidate at Rice. I'm the recipient of the NSF GRFP, as well as the Innovations Fellowships for this project. And I've worked in a variety of industries already, ranging from elastomers to biomedical. On our technical advisory board, we have Dr. Rafael Verduzco and Dr. Pulikal Ajayan, who are members of the Rice faculty who have worked extensively on these topics. So what I'd like to ask all of you today is that we are very early on in our module design. We would like to talk with you and find out what your pain points are, how we can best make a system that easily fits into your existing wastewater treatment or municipal water treatment systems so that we can make a module that fits your needs so you can solve this problem as easily and pain-free as possible. Our contact information is below. We'll be around all afternoon. And of course, you can find any of us on LinkedIn. Hope you have a great rest of the evening.
Thanks a lot, Jeremy. So with that, I'd like to introduce Elsa, Acosta, and Wonil Sohn out of the SHE Lab to talk about next generation cochlear implants to make sure that you can actually hear what we're talking about.
Hi everyone, we are Wonil and Elsa, and we are here to talk to you about the next generation cochlear implants. Cochlear implants are one of the most successful and popular cochlear neural prostheses available in the market. There is an estimate of 1 million devices implanted worldwide. These devices are intended for people who suffer severe sensory neural hearing loss, which is the most common cause of hearing impairment. Every year in the US, there are 65,000 patients who become candidates and get a new cochlear implant. And although the performance of these implants is between 70 to 80% of speech perception, this is only under quiet conditions. However, this performance is really impacted in more complex situations such as music encoding or with background noise. So cochlear implants have multiple components for sound processing, but the stimulation sites, which are between 12 to 24 electrodes in commercial implants, those are inserted inside of the cochlea, which is the blue snake-shaped organ that you see in blue. The idea with this is to bypass the damaged portion of the cochlea to activate with electrical pulses the auditory nerve fibers. There are two main categories for cochlear implants in the market. One of them is the straight implant. This has the advantage that it has the safest approach for the insertion. However, the electrodes are placed far away from the auditory nerve fibers that we are trying to activate. Therefore, there is some space for the spread of excitation, which causes the unwanted activation of neighboring frequencies. Actually, there have been multiple studies that report that even with electrodes with 22 active sites, the performance is only equivalent to 8 effective channels. Another type of cochlear implant is the precurved one. This has a precurvature before insertion, and the idea is to hug the core of the cochlea to be closer to the auditory nerve fibers. But the problem with this approach is that it involves a high risk of trauma in the tissue when it's inserted, and also because of the high variability of the cochlea, it doesn't ensure a tight electrode to neuron interface.
And with this, we hope to be able to combine the benefits of these two different types of electrode so that our electrode can form a safe and close interface to the auditory neurons for more focused stimulation. So we propose our multi-helix, high electrode density cochlear implant, as you can see in the schematic on the right. It is designed to form a close interface to the auditory neurons that are within the inner wall of the cochlea by expanding and closely fitting the inner duct. This also is designed to support up to 200 stimulating channel, which is 10 times the electrode density of current clinical electrode for richer quality of stimulation. And you can see that on the picture on the left, we have an image of our current electrode prototype that we were able to build with a thin film electrode. So our electrode design currently has branches in structures. So we have 25 branches extending to one side of the electrode that contain many electrical contacts to send out the stimulating current. We are able to construct this with polyimide that supports high channel density, and we further encapsulated this with protective biocompatible silicone to further protect the device and reduce any immune response to the cochlea. And our electrode can be easily rolled up into a more compact cylindrical electrode. So you can see that we are able to easily manually roll it up into a compact form. And this is possible without damaging the electrode because we use soft and flexible materials such as silicone. And after this, we encapsulate the device with a thin layer of biodegradable hydrogel to temporarily keep the electrode into its compact form. And the design and the dimensions resemble that of the straight clinical electrode. So we can use the same surgical procedure to safely implant it into the human cochlea.
Our strategy to mitigate the current spread is to have this unrolling mechanism and a special geometry that, as you can see on the demo video of a portion of the cochlea, is we aim to for the gentle placement of the electrodes near to the walls where the auditory nerve fibers are located. So overall, we have designed and fabricated a device that allows, through this special geometry and unrolling mechanism, a close interface between the stimulation sites and the auditory nerve fibers with the aim of mitigating the current spread. And all of this to take the most advantage of the high electrode density with 200 stimulation sites that our prototype has. All of this with the goal in mind of having a higher hearing resolution and stimulation specificity.
And then lastly, on what's next, we have two plans to optimize and validate our electrode. One is optimizing the mechanical properties to make sure that our electrode can be safely and reliably inserted all the way deep into the cochlea and allow the unrolling process to happen more optimally. So we plan to continue prototyping in 3D printed cochlea phantom and then move forward to testing in actual human cadaveric cochlea to verify that our electrode can form close and intimate interface to the auditory neurons for more focused stimulation. The other plan is verifying the result in animal studies using guinea pigs. So we will implant our electrode in cochlea, and we will also implant another recording electrode in auditory midbrain, so we can simulate our cochlea and measure the neural response, and we can map out the heat map of the area of neural activation to quantify the amount of current spread to demonstrate that our electrode can lead to more focused stimulation. So with these two plans, we aim to achieve a high-resolution, high-density electrode on a path toward a next-generation cochlear implant. With this, we would like to thank the cochlear implant team, our advisor, Dr. She, who provided guidance for this project, and also Dr. Zolotavin, who provided guidance for the fabrication of our electrode. Thank you.
Thank you.
And with that, last but not least, Barclay Jumet and Professor Dan Preston out of the Preston Labs for something that you might actually also be able to touch and feel if you go to the Rice Research Showcase later on.
Great, Adrian. Thanks a lot. I really appreciate the opportunity to be here. And I just wanted to take a few seconds at the beginning to say how exciting a time I feel it is at Rice Mechanical Engineering. We have a lot of really active and exciting research. In fact, we have 4 posters that you can check out in the room over here in the session immediately following this one. And we're also interested in translation. For example, at Greentown Labs, right across the street from here, we have one of our summer PhD graduates having founded a company that's already hired 6 employees and is continuing to grow. So again, really exciting time for us in Rice Mechanical Engineering, and today I'm excited to introduce Barclay Jumet. He's going to be talking about some of our work in collaboration between my lab and Marcy O'Malley's lab, our department chair. Barclay is a 2-time NSF fellow and also one of the Rice Innovation Fellows. So Barclay, please take it away.
Well, thank you, Dan. Like you said, I'm Barclay Jumet. I'm a 4th-year PhD student in Dr. Preston's lab. And today I'm going to be talking about our textile platform that allows us to incorporate wearable smart devices directly and seamlessly into our clothing. So one of the avenues that I'm going to talk about specifically today is using haptics and integrating that into our textiles, into our clothing. And haptics uses the sense of touch. Touch is one of our 5 senses, right? We have sight, we have sound, touch, taste, and smell. Of touch, there's so many different ways we can communicate information. It's the same way we know that our limbs are moving without looking at them. It's the same way we know we're walking on a wood floor or a concrete floor. It's just a diverse and a broad way to communicate information. And within that, there are tactile and temperature-based cues. We're probably most familiar with vibration. That's on our phones, on our game controllers, VRs, etc. We've also demonstrated not only vibration in a textile format, but squeezes like a blood pressure cuff, something very similar to that. Point forces, which you can imagine is just like a single point of pressure or force. And then we're also looking into cold and hot cues as well on the thermal side. One of the ways that haptics is being integrated into our lives more and more every day is in augmented and virtual reality. So augmented and virtual reality allow a way to sort of change the world around us, and haptics allows a third sense to be incorporated. So beyond our sight and our sound, we can use touch to really fully immerse ourselves into this technology and into these alternative worlds. It's often used in clinical aspects, whether that's for providing treatment or practicing as a resident, or even planning surgeries or seeing what sort of device could fit into a CT scan structure. And then, of course, there's the entertainment avenue where we have games, movies, concert, again, adding that third dimension beyond our hearing and our eyes. The problem with a lot of the current technologies in AR and VR is that they're relegated to the hand. So the hand is great because it has a really high density of what we call mechanoreceptors. So that means we can feel really well with our hands. However, if we're having our technologies in our hands, that means we can't really use them for anything else, especially activities of daily living, running errands, operating a car, scooter, something like that. And so one of the big holdups right now in haptic technology and augmented and virtual reality is being able to be mobile with it. And so that's what we're looking to solve today and going forward using our textile technologies. So in these clothing integrated devices, they're hands-free. In this case, we created a sleeve that goes onto the forearm. They're programmable, so we use fluids instead of electronics, much in the same way to program, in this case, a sleeve with 3 pouches that sequentially inflates. And then importantly, this is all done with a scalable fabrication process. This can be done roll to roll. It can be using CNC instruments like we do, a vinyl cutter here. And so this is really amenable to going out beyond the benchtop and out into the real world. So we had this sleeve, and we programmed it to provide this sequential directional cue. It's a very natural and intuitive cue that traveled along the forearm, both in the forward direction and in the backward direction. And we tested it on benchtop settings with many participants, and they had an 87% accuracy with just 20 cues of training. And then we saw with some participants a 100% accuracy of being able to direct themselves left, right, forward, backward, to be able to navigate the streets of Houston. And again, they had 100% accuracy with just a little bit more training. And so we demonstrated this in one of our most recent works, and we went over 2 miles of navigation on the city streets. We also tested an open field navigation, drawing Tetris shapes of all things, just using the sleeves to provide, again, those directions. So as far as the sort of markets go for this technology, of course, there are smart wearable devices like smartwatches and the like. There's the haptics realm in and of itself, and then, of course, there's also AR and VR, which I've discussed today. All of these markets are not necessarily codependent, but definitely integrated highly with each other. But in particular, we're really interested in the healthcare market for AR and VR. So I mentioned earlier, maybe this could be used for training during your surgical residency, which can often take many years just to perfect the craft. It can be used in planning these surgical operations once you are a certified medical doctor. You can then have patients use it. Again, in AR and VR, it allows you to be more immersed. So the patients will have a better time, they'll be more motivated, and likely see better outcomes in their clinical settings. And it doesn't even have to be at the clinic, it can also be at home by just having these low-cost technologies that are made out of textiles. So with that, I'd like to thank my lab, the Preston Innovation Lab under Dr. Preston, and the Mahi Lab, who we collaborate quite closely with. Without their help and their insight and their contributions, this would not be possible. So thank you.
Thanks a lot, Barclay. On this stage today, you saw projects, individuals that may be the next CEOs of some of the companies that you know today. Starling, sitting just right down there, was on a stage like this just a few short years ago. Syzygy, Dexmat, Helix Earth Technologies just across the street were all run and founded by and based off of technologies out of Rice Labs, just like the ones you saw today. And if you'd like to learn more, go see the Research Innovation Showcase in there, or go speak to any one of the speakers or to myself. Thanks for listening.
Appreciate it.